Good morning, folks. It is a crisp early December morning here on Cape Cod, and it is the third episode of our AP Calculus Free Response Question Advent Calendar. Let's open up the third door of this chocolate Advent calendar and then do some calculus. You know the routine. Let's find number 3. There's number 4. Where is number 3? All the gold here kind of blends in, makes it really hard to read. There is the 3. I see a little white ball there by number 3. Let me zoom in here. So we are near the bottom of the calendar at number 3 with these happy little bears. Is it going to be a bear or a ball? I guess it's probably going to be a ball. I will put today's free response question on screen now so you can read through it while I open up this compartment and try out this chocolate. What have we got going on here? I'm eating way too many sweets this month. Look at that. It is a white ball. Will this be white chocolate? I don't know. I don't know exactly the nature of everything that this contains. Looks like it's just another normal piece of chocolate. Oh, wow. That just split in half very easily. It has something inside of it, probably chocolate. That is probably my favorite chocolate so far. God, this is all so sweet to be eating right in the morning. Let's do some calculus. This is problem 5 from the 2000 AB exam. Let's read it. Consider the curve given by xy squared minus x cubed y equals 6. The first part of the question is to show that dy dx equals this fraction. So we're just going to have to do some implicit differentiation and make sure that our result matches the answer given there. This is a no calculator question, so we won't be graphing this or anything like that, but I went ahead and graphed it anyway, and I'll show you what that looks like just because it's interesting. We will, of course, not appeal to this graph during our solution, since that's not allowed, but that's what it looks like in case you were curious. Pretty cool. All right, so let's go ahead with our implicit differentiation. I will just rewrite the equation here. We have xy squared minus x cubed y equals 6. And what we're going to do is take the derivative with respect to x on the left side of the equation and on the right side of the equation. On the right side of the equation, of course, the derivative, I'll put that this is part A as well, the derivative of a constant, the derivative of 6, is just 0. On the left, we'll have a little bit more going on. We're going to need to apply the product rule, in fact, because this first term is x times y squared, and this second term is x cubed times y. So let's start with xy squared. If we call x our f and we call y squared our g, then the product rule, of course, here is f prime g plus g prime f. F prime is just the derivative of x, which is 1, so f prime g is just y squared. And then we need to add g prime f. G prime, the derivative of y squared, is going to be 2y, that's like the derivative of the outside function, 2y, but then y is itself a function, so we need to also use the chain rule here, and that's where the signature dy dx of implicit differentiation comes from. It's like the derivative of an inside function. So that is our g prime. Let's not forget that we have to multiply that by f, which in this case is x. Let's move this equals 0 over to the right because we're going to need a little bit more room. Now we have to take the derivative of x cubed y, and this whole thing is getting subtracted. So we will subtract this derivative. Now again, we're applying the product rule. F is, I should probably put this a little bit differently so you can see the exponent there. F is x cubed, right? So f prime is going to be 3x squared. And so f prime g is 3x squared times y. Remember, the dy dx terms only show up when we take the derivative of y. So it's going to show up in this next part where we have g prime f. G is y, so g prime is literally just dy dx. And then we have to multiply this by f, which is x cubed, and close the parenthesis. Remember, we're subtracting this whole thing. And this is equal to 0. Now we just have to solve for dy dx. Solving for dy dx is super easy. You can do it step by step if you need to, but I think it's really easy to just do this in one fell swoop. I'll show you how I think about it. So I'm going to write dy dx equals, what does it equal? Well, the first thing I would do is move all the non-dy dx terms to the right side of the equation. For example, y squared needs to get subtracted from both sides. So there's going to be a minus y squared over here. What else do we have without a dy dx? The only other thing is minus 3x squared y. So we would have to add 3x squared y to both sides. After we move everything without a dy dx term over, we have to divide by everything that's with a dy dx term. Really what we do is gather those terms together, factor out the dy dx, and then divide by everything else. So in this case, that's going to be a 2yx that we see with a dy dx. That would get divided, so 2yx. And then we also have a minus x cubed getting multiplied by dy dx. So we'd also have minus x cubed in the denominator. And that's how we solve for dy dx. Now we just need to make sure that this matches the answer that was part of the question. And if we scroll up, we see we're supposed to have 3x squared y, yes, minus y squared, yes, divided by 2xy, yes, we have that, minus x cubed. So there we go. I will take one last step of just rewriting this exactly as it appeared in the question. All right, let's move on to part B. We are supposed to find all points on the curve whose x-coordinate is 1 and write an equation for the tangent line at each of these points. So we'll take the original equation, defining the curve, and replace x with 1, and then find all the possible y values. Those will tell us the full sets of points where the x-coordinate is 1 on this curve. I'm switching to purple here just for kicks, so let's rewrite this equation, but replacing the x's with 1s. So that's going to give us y squared minus y equals 6. And now we just have to solve this quadratic for y. Let's subtract 6 from both sides, so y squared minus y minus 6 equals 0. And then we can factor this into y minus 3 times y plus 2 equals 0. We know this factorization works because minus 3 times plus 2 is minus 6, and minus 3 plus 2 is minus 1. So we see this is a correct factorization. And this gives us the possibilities that y equals 3 or y equals negative 2. That, of course, is just the zero product property. So now let's come over here and write our tangent lines. We will do the tangent to the point 1, 3. Remember, this came from x equaling 1, so that's the x-coordinate. And then we'll also find the tangent line at the point 1, negative 2. Now, at the point 1, 3, using point slope form, we of course would have y minus 3 equals the slope, which we'll have to find, multiplied by x minus 1. Now, to find this slope, we're just going to plug this point into the derivative dy dx that we found in part A. And I'll put that in red right down here. So what we're doing is taking dy dx and we're plugging in x equals 1, y equals 3 to find the slope at this point. And remember, dy dx is right up there. So that's what we're plugging this stuff into. So what is this equal to? Well, x squared, if x is 1, that's just 1. So this is just 3 times y, and if y is 3, then 3 times y is 9. And then we subtract y squared. Y squared, of course, is 9. In the denominator, we have 2xy, which would just be 6, minus x cubed, which would just be 1, and so this is 0 over 5, which of course is 0. So we can throw a 0 in here as our slope. Turns out this equation would actually just be y equals 3 then. And we can put this in a box and move on to the next tangent line. The next tangent line is at the point 1, negative 2. Again, we can start with point slope form. Y minus the y coordinate, that's y minus negative 2, which is just y plus 2. This has to equal the slope, which we'll find in a minute, multiplied by x minus 1. To find the slope, of course, we'll just plug this point, 1, negative 2, into the derivative, just like we did before. So we are now plugging in x equals 1 and y equals negative 2. What is this going to equal? Well, the derivative says we have 3x squared y first. X is 1, so x squared is 1. Y is negative 2, so 3y is negative 6. And then subtract y squared, so in this case, that's minus 4. In the denominator, we have 2xy, which is just going to be negative 4, and then subtract x cubed, thus we'll subtract 1. Negative 6 minus 4 is negative 10, and the denominator is negative 5. So this is negative 10 divided by negative 5, and so the slope is positive 2. And so we can replace our box with the slope. Turns out it is 2, and so this is the tangent line. Y plus 2 equals 2 times x minus 1, and we can leave it in point slope form. All right, it is on to part C. Find the x-coordinate of each point on the curve where the tangent line is vertical. That means the slope is infinite, so to speak. So to find where that happens, where the tangent line is vertical, we're going to need to see where the denominator of the derivative is equal to 0. That's what will make it infinite if the denominator is 0. Then we just have to check that where the denominator is 0, the numerator is not also 0. As long as the numerator is anything else, we'll be fine. So let's begin by setting the denominator equal to 0. The denominator of our derivative is 2xy minus x cubed, so we have that 2xy minus x cubed is equal to 0, and thus 2xy equals x cubed. We can actually just divide both sides of the equation here by x, because if we come up to the definition of our curve, it's given by this equation, and if x was equal to 0, this equation would never be true because 0 minus 0 does not equal 6. So x cannot be equal to 0, thus it's totally fine to divide both sides of this equation by 0. Thus we have 2y equals x squared. Again, this is the denominator of our derivative, which only applies on the curve, and on the curve, x is not equal to 0. From here, we can divide both sides by 2 and find that y equals 1/2 x squared. So where is the tangent line vertical? Well, it's vertical on the curve where y equals 1/2 x squared. So let's go back to our original equation and replace y with 1/2 x squared and see what x values come out of that. One more time, what we did was set the denominator of the derivative equal to 0. That led us to this, y equals 1/2 x squared, but we're only interested in points that are actually on the curve. So we're going to plug this into the curve and see what x values will satisfy this. This is the original equation. Let's go ahead and replace the y's with 1/2 x squared. So first, we're going to have x times 1/2 x squared squared, which is 1/4 x to the 4th. And then we're going to subtract x cubed multiplied by 1/2 x squared. I'll put that in parentheses. This, of course, equals 6 on the right side of the equation. X times 1/4 x to the 4th is 1/4 x to the 5th. And then minus x cubed times 1/2 x squared is minus 2/4 x to the 5th. I'm just rewriting 1/2 as 2/4 because I want common denominators. And this equals 6 on the right side of the equation. Now we can go ahead and combine these on the left to get minus 1/4 x to the power of 5 equals 6. Multiply both sides by -4, and we have that x to the 5 equals -24, and thus x is the 5th root of -24. We can't take the square root of a negative, but we can take an odd root of a negative. So this is defined. This is a real number. So it appears we have a vertical tangent where x equals the 5th root of -24. However, we do need to verify that the numerator of our derivative is non-zero here to confirm that we actually have a vertical tangent. We need to make sure the numerator of the derivative is non-zero. We know that x is the 5th root of -24, and we can plug that into this equation for y in order to find the appropriate y coordinate. Remember, we assumed this equation for y was true and plugged it into the original equation for the curve to get this x value. So to get the y value, just plug this x into this equation for y. Then we'll plug the x and y into the numerator of the derivative. The numerator of the derivative, for your reference, is 3x squared y minus y squared. When we plug this value for x into this equation for y, this is what we get. 1/2 x squared, so the fifth root of 24 becomes 24 to the 2/5. The negative goes away because of the squaring when we plug in for y. So you square that, negative goes away, and it's just 24 to the 2/5 with that 1/2 out front. Then we plug this value for x and this value for y into the numerator of the derivative. That gives us 3 times x squared. Squaring x again gets rid of the negative, so we just have this, multiplied by y, which we see here. And then we subtract y squared, which we see here. Squaring y turns the 1/2 to a 1/4, and the 24 to the 2/5 becomes 24 to the 4/5. Now this is clearly non-zero because it's clearly a positive number. Because what we have on the left is 3 halves, 24 to the 4/5, if you were to combine those, 3 halves, 24 to the 4/5, and we're subtracting a smaller number, 1/4, 24 to the 4/5. So we've got 3 halves, 24 to the 4/5, minus the smaller number, a 1/4, 24 to the 4/5. So clearly this is positive, and more importantly, that means it's non-zero. So indeed, x equals the fifth root of negative 24 is the x coordinate of a vertical tangent. And that completes our solution to problem 5 of the 2000 AP Calc AB exam. Let me know in the comments if you have any questions, and please consider joining Wrath of Math as a channel member to help me create more high-quality calculus content and to get access to exclusive videos and other member perks. I'll see you tomorrow to continue our advent calendar of AP Calculus FRQs. Thanks for watching.